I think that we are ready to start. Um, welcome everyone to this webinar. The title of today's webinar is Physical and Social Vulnerability for the Multi-Hazard Analysis of Components and Systems. This is the third webinar around the MEDiate project. We will have a panel of speakers that I will introduce in a moment. Just before we go in details into today's webinar, we just want to mention something related about school infrastructure and the impact that recent natural hazards, such as floods, have had in this type of infrastructure. In particular, it's worth to mention what happened in Valencia recently due to the Dana storm. We all saw the different damages on infrastructure, the losses of lives, and how devastating this event was in the city of Valencia. And in particular, we can also see the impact that this had in education and in particularly in school infrastructure. So here are two different news items, one from Levante, one Valencian newspaper, in which they mention that around 11,000 students from 22 schools and institutes are still out of education 1 month after Dana. So this is to mention the impact of one specific event can have a very long-term impact in community and societies, and in particular in children. This other news item also mentioned about 92 schools completely destroyed, and all the students that were attending these schools with no capacity to go to the schools and have a proper education. This happened something similar very recently here in the UK. For instance, the storm Bert, which happened a week ago, just damaged one school that was recently reopened because it was in repairs due to a previous flood event. So the students were not able to come after a long of time of interruption of education. And the same happened in Oxfordshire, where different schools were shut down during this event and some days after. So this is just to mention that impacts of disasters due to natural hazards, and in particular in these both cases of floods, are not something that only happens in developing countries. Even in the UK, in Spain, the climate change and these events are impacting day-to-day lives and educations and school infrastructure in this case. Just before going and giving the word to our panelists, just to mention that in our series of the UNESCO Chair, we have several additional webinars already scheduled. In December, Professor Mohammad Shamsuda will talk about the salinity crisis and the challenge in saline water and soil in coastal Bangladesh. He is a professor in the IDRD in University College London. For January, we have Professor Solveig from University of Iceland. She will be talking about infrastructure resilience and how different models such as system dynamics and agent-based modeling can be used to assess this resilience. In February, we will have Professor Solomon Tesfamariam from University of Waterloo talking about tall timber design and the interaction between earthquake and fire loads, what has happened and how the design is shifting in the future. In March, we have also a very interesting webinar by Dr. Sinan Akar from T-Rob Technology. He will talk about the different approaches from the academic community and the professional community to model catastrophes, and in particular, this type of models associated with the insurance industry. And in April, we will have Dr. Sonia Giovinazzi from ENEA talking about a multi-criteria life cycle approach to improve school infrastructure in the Kyrgyz Republic. So without further ado, let me introduce the speakers today. First, we will have Dr. Pierre Gell, Dr. Gell has a PhD in civil engineering from University College London in 2016, and currently he is working as an earthquake engineering expert at the French Geological Survey, BRGM. We will have also Dr. Asana Paramal-Pateri, also a former PhD student at UCL. She is currently a postdoctoral researcher in UNESCO chair, and she has worked mainly on school infrastructure and how to use Bayesian network to analyze risk. We will also have a brief intervention by Professor Dina Dayala. She is the UNESCO chair in disaster risk reduction and resilience engineering and full professor at UCL. We will have Dr. Konstantinos Trevlopoulos, also an earthquake and volcanic risk researcher at VRGM. He holds a PhD in earthquake engineering from University of Thessaloniki. We will have Dr. Katerina Negulescu. She is also working at VRGM. She holds a PhD in seismic risk vulnerability assessment of building constructed in Bucharest and obtained from the um, Technical University of Civil Engineering in Bucharest. And finally, we will have Dr. Nadisha Wanigaratna. She is a senior lecturer at Anglia Ruskin University. And she is contributing into the construction economics and natural hazard induced property loss assessment in the MEDiate project. So well, you are very welcome all. We're very happy to have you. Thank you very much for accepting to participate in this webinar, and thank you to all our attendees. If you have any questions during the lectures, please just go to the section of Q&A and type those in there, and the panelists will answer once they finish their session. So thank you very much, and Pierre, please go ahead. The word is yours.
Thank you very much, Rafael, and thank you, Dina, for the invitation. Yeah, sorry, I'm just, yeah. Okay, good. Yeah, so thank you for the introduction. So I'm Pierre Gale from BRGM, the French Geological Survey. And I will just start, let's say, this session by discussing a few aspects on introducing the subject and on the modeling of multi-hazard vulnerability with some state-of-the-art consideration and some pending issues that we identified. So first of all, some of these results here have been, let's say, achieved or completed during the European project MEDiate, which focuses on the development of a decision support system for disaster risk management by considering multiple interacting natural hazards and cascading impacts, while also accounting for forecasting modification in the hazard and exposure. And as you well know, that the construction of multi-hazard impact scenarios constitutes a major challenge, which reinforces the need for an adequate vulnerability modeling that integrates multi-hazard integrations. And in this short presentation, I will just cover a few topics as an introduction, like a recollection of main principle of fragility modeling, some comparison of existing practices of fragility vulnerability modeling for various hazard types, also discussing the various types of multi-hazard interactions, discussing possible formulation of multi-hazard fragility models, and then discussing some challenges that are still, let's say, left here. So I think first, I think most of you know that when we talk about fragility and vulnerability models, we should first be clear that when we spoke about a fragility model, we are really speaking about a probability to reach a given damage state or for a given demand to exceed the capacity of the structural system given the intensity. So this is let's say this sort of representation on the left of your screen. And really on some hazard types, they are really used to deal with vulnerability functions, which are more like a deterministic functions that directly relate intensity to let's say to a given loss ratio and so on. And again, there are various ways to derive fragility models. Like I think most of you know that you can use empirical approaches using damage data for past events, analytical approach, for instance, based on simulations or numerical models, or sometimes when let's say the collected data is sparse, or you can really not really, let's say, model the physical mechanism, you may rely on expert judgment approaches. And finally, there are some hybrid approaches, for instance, that can merge, let's say, maybe some analytical models with new empirical data, for instance, by using Bayesian updating. And usually, when we speak about a fragility model, we have to consider, let's say, a set of components, or let's say ingredients that you need to consider. Like first is the intensity measure. Let's say like there's a set of variables that are representative of the hazard loading. And also, let's say what is the damage state that you want to estimate, or for instance can be a qualitative scale, or also can be maybe defined quantitatively by the exceedance of a given engineering demand parameter. And then your function also has to be related to a functional form. So usually people just use a normal cumulative distribution of the logarithm of the intensity measure. And also, of course, your model has to be related to a given asset type, a family of buildings, or one type of building, and so on. So also with the associated uncertainties related to this. So again, when we speak about fragility, we speak about these fragility parameters like the median and the standard deviation. I just now going to discuss really just very quickly some single hazard models for different hazard types. So regarding seismic fragility models, this is just a really non-exhaustive list, let's say, of recent and maybe probably useful resources that have gathered lists and compendiums of seismic fragility curves. For instance, from the European project Synergy, you can find some reports and still, I think, online resources on a compendium of fragility curves for RC and masonry buildings. Of course, you have the vulnerability database from the GEM Foundation, also with fragility functions, vulnerability models, damage to loss models as well, and a set of pushover capacity curves for different types of building classes. And also more recently, the European project CIRA, with this CIRA review database, again, with a lot of capacity, fragility, and vulnerability curves. And this created the basis for the development of the European seismic risk model. So now it is becoming convenient to use this GEM taxonomy of buildings, because you have all this set of collapsible attributes, for instance, that are relevant to the seismic performance of different construction type. Also, you have always, let's say, some debate and issues about the selection of adequate intensity measures, which should be efficient and sufficient among other, let's say, requirements. And again, also the choice of the damage scale is always important also, and also there's a widespread use of the European EMS 98 damage scale, especially for empirical fragility functions in Europe. Regarding flawed fragility models, let's say you may also, let's say, distinguish vulnerability models between two approaches. You can let's say have a physical approaches that really rely on hydrogeological models to estimate flood hazard, and then you let's say you compute the economic consequence for a given event or a catchment area, or based on a damage index. Also, you may just use a parametric or empirical approaches that use a set of quantitative or qualitative indicators that rate the vulnerability of a building or an area. But this is, let's say, a bit decorated with the hazard intensity. In a flood risk assessment study, there is let's say, a strong use of empirical approaches, so relying on a post-event damage data collection. And this leads, let's say, to let's say a wide use of vulnerability functions and very few examples of fragility models, as we have seen in the seismic hazard case before. And then in case of intensity measures, most of them are flood depth and flood velocity, can be used as a single variable or a combination. And here again are a list of, let's say, some useful resources. So some papers gave an overview of existing approaches. You have also the global flood depth damage model released by the JIRC, and also the Parnassus procedure that will also be discussed later on by Asana. So I just don't describe it here. And also I just finish here for single hazard model with an example also of a mass movement vulnerability models. Also here, some people speak about a landslide vulnerability models, but also there is a first need to distinguish between a debris flow events. If it's just, let's say, a moving mass that, let's say, will impact the building's facade, then you can relate it to the flow height or volume or the pressure applied on the structural system. Also, you can, the second case is also when you're speaking about slow moving landslide events that can maybe happen as a ground failure or differential settlement under the building. And you have to look at differential displacement or deformation rates. And here again are some examples of debris flow vulnerability functions that are based on, let's say, some on let's say, experienced or based qualitative description of the intensity of the hazard, indicator-based models as well, which use expert judgment indicators, data-driven models, damage-driven models, sorry, again based on damage observations, and also mechanism-based models, which are based on numerical models, are quite scarce. And especially if you want to consider, let's say, a wide range of different building classes and so on. Let's say if you want to copy what is done in the case of seismic hazard, for instance, there is still not a lot of models like this. Yeah. And also there is the issue of damage scale, for instance, and there is also a paper that reviewed all these existing damage scales for debris flows. Let's say most of them contain 5 damage degrees, like in the case of seismic hazard, but also they lack precision in terms of description of the damage states and so on. Now I'm just moving to the case now of a proper multi-hazard risk analysis, and also how we can consider multi-hazard interactions. There is a classification that exists on, let's say, 2 main types. They are called first one level 1 interactions that represent natural interactions of hazards independent of the presence of the physical component, or level 2 that are only focusing on the interactions that the hazard have on a given to the existence of a given site, component, or infrastructure. So this is some level 1 interactions that have been considered, for instance, in the MEDiate project. So I will not go through them all, but you can go to a quite, let's say, complicated classifications with a lot of different situations between different types of hazards and so on. And here, in this session, I think we are really focusing on level 2 interaction, the effect of different hazards, but always through the perspective of a structural system. So we are not really, let's say, investigating if the hazards were dependent, correlated, or independent. We are just focusing on the effect that they may have, combined or not, on a given structure. And In terms of level 2 interactions, then you can have a different fragility formulation. So this is a different cases actually of types of fragility models you could have based on the if you have single or multiple hazard events, if you use single or multiple intensity measures, if you have a different failure modes or only one in your structural system. And so this is very simple case. For case one, single hazard, single intensity measure. Then you can have a case two with a fragility surface because you have multiple intensity measures. Case three is a multiple failure modes. You can have a system fragility functions. And then moving on to the more interesting part is the case when you have multiple hazard events that are combined into multiple intensity measures, multiple failure modes. You can have a multi-hazard fragility functions. And case 5 is a bit similar, but it's more like when you have a temporal aspect, temporal dimensions with a time-dependent framework, and initial state fragility and a damage state dependent fragility. So this is why we can actually, let's say, we see, let's say, two main types of modeling multi-hazard fragility. First would be through the way of damage state dependent fragility models, where you have, let's say, an intact state of your structure, and then you have a first event that gives you a set of damage, and then you have your let's say conditional fragility model based on the also pre-existing damage state. So here are a few examples. The first one is for a main shock aftershock sequence in the case of earthquake hazard. And the second one that will be explained by my colleague Katerina later on the cascade scenarios also for earthquake tsunami to the reduction of pushover capacity curves. And then the second possible formulation for multi-hazard fragility models would be through the use of vector intensity measure fragility models when you have, let's say, joint loadings. So this first example, I like it a lot because I think it was one of the first papers that used the fragility surface to tackle the case of multiple hazard risk. It was by Lee and Rozowski on the failure of wood frame buildings with combined snow and earthquake loading. And also here also is an example of dike failure exposed to earthquake and flooding also. And now I just finish with, let's say, a set also of pending issues also that remain that maybe will also be discussed in the following presentation. So first one is the characterization of a multi-hazard exposure. So we have seen that in the case of earthquake hazard, we have exposure models that have been established recently, like the exposure model from the ESRM 20 that is available now at European level, besides also national level databases that are quite exhaustive based on the GEM taxonomy. But also regarding other hazard types, sometimes, let's say, existing fragility models are not very, let's say, precise in terms of the structural parameters they require. So there is maybe one could say there is less pressure to establish a detailed exposure database. And so maybe there have been less effort on this part. And many parameters that may be relevant to these hazard types. For instance, the roof type, foundation type, and so on are not present in the GEM taxonomy. So also this constitutes an opportunity to make use of this GED GED for all multi-hazard taxonomy. Here is an example of the different attributes on the right. But still identifying and inventorying all these relevant parameters for a given area remains a challenge. Second issue would be also the harmonization of damage states. For instance, here you have the EMS 98 damage scale in the case of earthquake. There have been some effort also to define some damage scales, for instance, for flood, tsunami, wind. Here also we have a paper by Maywald and Schwartz on this subject and trying to make them let's say, harmonized and try to, let's say, make them fit between the different. Also, this is something that is quite difficult also to understand and to apprehend. When you have to harmonize outputs from different fragility models. And maybe a potential solution would be to focus on functionality states. For instance, if you have a given object, like here in the case of a highway bridge, you can check for different hazard, earthquake, flood, ground failure, which component of your structural system is susceptible to which type of hazard, and then you can build a different functionality level depending on the type of failure your structural system has been exposed to, and then you have to think in terms of consequences for this object. And maybe some failure mechanisms will have been quite a strong effect or not. And through these consequences, you can harmonize your functionality levels and all the physical damage states that may lead to it. And then you can really assemble this in the terms of multi-hazard fragility, but based on the functionality. And finally, one last issue also is the use of these state-dependent fragility models that we have seen. And they are quite appealing because they can be used in let's say a Markovian framework. This is an example here of such a framework where you can really analyze and simulate the multi-hazard life cycle consequence analysis of a given structural system with different possible events occurring through its lifetime. And then through the use of transition matrices here on the right, you can just evaluate at each step the probability to go to different limit states and so on. And these conditional probabilities are really, let's say, make a nice fit with the concept of state-dependent fragility curves. But maybe one question that we could ask also is the importance of the loading history in the order of the hazard sequence also. If one limit state has been caused by, I don't know, flooding or earthquake, will it be the same then for the history and the behavior in the next steps of the structural systems, for instance? And I just finish with, let's say, a few points. So we have seen that there is a large disparity of approaches and level of maturity between hazard types. And also maybe we should keep in mind that the adopted modeling solutions, they depend also on the objectives of your vulnerability assessment. Let's say if you just want to focus on the risks analysis through the lifetime of a given asset, also, or maybe just do a multi-hazard risk scenario for a given area, then maybe you will not use the same fragility and vulnerability modeling with the same objectives also. One thing also to point out is that there are so many possible hazard interactions, so this also will lead to a myriad cases requiring specific fragility models each time for each possible combination. So also this is something to have in mind. And also, regarding these functional consequences that we have seen to the harmonization of damage states, also this could also be done in the light of social vulnerability analysis, and maybe which parameters are actually important for these types of analysis. Okay, thank you very much. I'm finished now. I'm really sorry. Maybe I took too long.
Perfectly all right. Thank you very much, Pierre. Maybe
Thank you,
Asana,
Dina.
if you want to share your screen and start your presentation. You need, yes.
Yeah.
Perfect. Thank you.
Hello, everyone. Hope you can see and hear me well.
Yes.
Yeah. Okay. So thank you, Pierre, for the introduction presentation. It puts all of our presentations in perspective. I think in this presentation, we are going to focus on empirical and analytical methods for fragility and vulnerability function generations. for the urban scale of residential building stock. We have a small delegate also joining, so if you hear something in between, don't. So the first part of the presentation, I'll be talking about the flood vulnerability assessment, and then Dina will be talking about the seismic fragility assessment. So as Pierre mentioned, this as part of the MEDiate project, we have analyzed a part of the Nice building stock, focusing on masonry buildings, using the Parnassus approach for empirical flood vulnerability. So this approach was originally developed in 2010 onwards in versions starting from one for historic city centers in the UK, exposed to flood hazards, and then was updated again for specific structures like churches and schools in the Philippines. And more recently in 2020, the work in Kuala Lumpur, again on historic city centers and schools. So this latest version was then applied to Nice in France as part of the MEDiate project. And certain aspects that were utilized along with the Parnassus approach was to go for a virtual data collection and then a Monte Carlo simulation to generate empirical vulnerability functions. So we will go through this in this presentation. So Parnassus approach is a parametric vulnerability-based vulnerability assessment approach where we have a set of parameters that define the performance of a building exposed to the hazard. So in this case, flood hazard. And the parameters are defined based on how the building performs when exposed to such hazard. So these can be related to the size of the building, say, for example, the number of stories, hence the weight of the structure put on the ground, the footprint area, the susceptibility of the water being getting into the building, which depends on the height of doors or windows. Similarly, the conditions on the outside of the building, for example, the surface condition, which can be paved surfaces or unpaved, which very much matter for the purpose of water being retained in the surface. Again, if there is a availability of drainage systems and any specific flood prevention features. So again, in the case of flood hazards, the performance also depends very much on the level of base of the structure with respect to the road surface or the ground adjacent to the building. So this is also depends on whether the ground floor of the building is raised or is it below the surface of the road surface, for example, if you have a basement. So these parameters directly affect how vulnerable the building is to the floods. So the set of parameters has been updated for each version of Parnassus for the case-to-case basis. So how do we then use the parameters to define the vulnerability is what we're going to discuss in this presentation. So we start with this, we know there is this locality exposed to floods. That's where we are going to start our vulnerability analysis. And then what we want to reach is the estimated losses or replacement cost, as we would try to estimate from the vulnerability assessment. So in this particular process, we have tried to go for virtual data collection, which is very useful when you are not having enough resources and time to go for a direct field data collection. Which will be useful to then garner or gather the attributes of these parameters that we just saw at individual building scale. But as you can imagine, this has some limitations and advantages, where you can map, you can cover several number of buildings in a short amount of time, but at the same time having limitations on the certainty of certain parameters that you can get. So what we did in this case is, instead of just looking at all of the buildings one by one, we sample a set of buildings to then understand the distribution of these attributes for the parameters. which can define the distribution, probability distributions of these parameters, based on which we can then run a Monte Carlo simulation, which generates any number of samples of representative buildings. So these will then give us a sample of a representative sample based on which we can then calculate the vulnerability function. So on that simulated building sample, we would calculate vulnerability ratings, which I'll explain in a bit, and following which we can compute the vulnerability index for each of the buildings and as a cumulative for the sample altogether, which we can then use to compute the replacement cost or the losses. So just to go through the steps in a bit more detail, we start with identifying a locality that is exposed to flooding. Like hazard maps such as this are available for most of the locations, although it needs updating with the time. So we identify some locations which are known to be susceptible to floods. And then we can have a detailed or closer look at these locations on any of the open map source platforms, where you can really go in depth and look at street level at individual buildings. So this is very useful where we have the street maps available anywhere in the world, and quite a bit of detailed information is already available, such as we will see in the following slides, which are very specific to the flood vulnerability assessment. So as you can see there, we can keep looking at buildings one by one on along a street, or we can then sample from a given locality and look at specific number of buildings. So as we saw the number of parameters, in this version of Parnassus we used in Nice, we were looking at 13 parameters. Each of these have a certain distribution. As we can see, the parameters like the number of stories, a footprint area, this varies in a range, say because we're looking at masonry buildings. The number of stories we're seen to vary between 1 to 4. Roof height, for example, is not taken as a separate parameter. This is taken as a factor, as a function of the number of stories for ease. And similarly, we have the remaining parameters, including the surface condition, building fabric, height of doors, windows, and plinth with respect to the road surface. So what we did in the first instance is to look at 50 masonry buildings to understand the distribution of these attributes in the sample of buildings in Nice, to then characterize the distribution of each of the parameters, each of these vulnerability parameters. So certain variables which has a discrete nature were assigned just direct probability of occurrence of such attribute. For example, we have more two-story buildings as compared to a single story or more than 4 stories. Similarly, footprint area, which is a bit more continuous distribution, which was characterized with a normal distribution with given mean and standard deviation. And each of these, we can then take these parameters from the street view as we saw before. So it was also useful to look at the top view of some of these buildings to gather things like the footprint area or the perimeter of the building. Again, there are other parameters which are directly observable, sometimes not so directly observable. So there are also more information that is available if we look in the wider picture. Say, for example, the surface around the building or the level of building with respect to the road surface or the availability of drainage. So this is what I meant by there is a lot of information that's readily available, free of cost, and can be gathered in a reasonable amount of time. ready for our analysis. Again, things like height of window and plinth and door. This is probably the parameter that has the most uncertain nature, because we are not going to measure directly from the images, but with relative to the actual building, it is possible to come to a reasonable value. Again, these are given continuous distributions with normal distribution. So once we have these, we can then generate, we then generated about 500 buildings through Monte Carlo simulation. And each of these buildings will have a vulnerability index, which is nothing but the sum of all the vulnerability ratings of individual parameters. Like you can see in this table, each of the attribute has a certain vulnerability rating. So summation of all the ratings will give us the vulnerability index. So we can then use the cumulative function to compare with available such functions for different localities. Sorry about this. Sorry. I'm sorry, Dina, would you like to take over?
Yes,
Sorry.
if you can keep pushing the buttons. Okay, so here we are now at the estimation of the economic losses, but sorry, I need to so thank you, Asana. And we basically look at a replacement cost for the buildings, a damage factors, a vulnerability factors, which is the element that Asana has just illustrated so far, and the footprint area of the building. One of the most complex things to define is the damage factors, and in this particular the damage function that we're seeing here, as already also introduced by Pierre, we looked at the distribution of more than 25 different the depth damage function and regress them in order to have one that could be used relatively widely for many different location and typology of buildings, and we compare this with the one that is available in the Huizinga model that done by JRC, where we can see that our damage ratio is slightly higher in the 0 to 1 meter depth, but then it becomes less, it's moderated in greater depths of water, because typically most of the damage will be done in the first and second, and then it sort of flats out. On the other end, we want to look at the total replacement cost. So this is both the cost of the buildings, but also the cost of the contents. We can use a different value factor depending on the type of construction and also on the type of contents and for the type of use. In this particular case, which was, and as you can see here, that we are using three different factors for each of them. In this particular case, we have used a reference from Europe, because this was within the MEDiate project, which is applicable to European nation, of 1,543 euros per square meters. That done, then we can bring together those equations, and then we can look at what would be the replacement cost depending for that portfolio of buildings with the randomization that we have done, and therefore with the distribution that should be representative for that particular area of Nice, which of course includes many more than 500 buildings. So this is just a let's say normalized to that number of buildings, and we can see that of course the scenarios are very different and the losses are going to be very different, whether you have 50 centimeters water depth scenarios or 1 meter water depth scenarios. And we can see here that because, as we also saw from some of the pictures that Asana showed, we have buildings that are below the level of the road level and therefore below the ground. The 1 meter scenarios can result in depth of water that are up to 1.6 meters and or 1.5 meters, and in that case clearly the damage is quite substantial. And these of course, these replacement costs, however, are cumulative costs, basically. I think that with this we conclude the part. Thank you very much, Asana, for keeping pushing the button.
Thank you. Thank you, Rina, for completing this.
We conclude the part on the floods, and please, if you want to progress to the second part. Yes, here we are talking about seismic fragility, and I will go very quickly because Pierre has already introduced all the relative concepts, so we will just want to mention the fact that this idea of using location-specific exposure data is quite important, even though you can then generalize at larger level, and some data collections needs to be carried out in order to determine reliable fragility functions. In this particular case, we use an analytical approach rather than an empirical approach, as we have just seen. We use a model that is called FAMIVE, which we have already introduced in previous webinars. So please, if you want to know more, go back to our UNESCO chair page and look for it. The system is based on limit state analysis and on performance displacement methods, and it's applicable to different typologies, but basically and mainly to masonry structures. I will illustrate these 6 points. So Asana, if you want to quickly progress. Yes, so the procedure is to identify a certain number of buildings. This was a case that we developed for Valencia, which I will get into a minute, together with colleagues from Politécnico de Valencia and Universidad de Alicante. We then use the data that we have collected through FAMIVE to determine their collapse load factors. Having determined the collapse load factor, we can identify by type of mechanism different typologies. When we have the typologies, we can then reduce them to a 1 degree of freedom oscillator from which we can characterize some capacity curves, and then the capacity curves together with intersected with an elastic or inelastic spectra, whether natural or synthetic, we, through the N2 method, can take us to define fragility functions. And once we have fragility functions, we can then introduce the concept of seismic risk and compute the risk for a given time horizon. Asana, please. So the benefit of this approach is that we are considering a library of several different failure mechanisms, which allow us to consider many different construction typology and construction solutions. Please, next one. These are the details, if anybody is feeling like studying them in details, for some of them at least, from the numerical point. So, yes, please go ahead. And I would like now to show you how the procedure is applied to the city of Norcia, which was affected by an earthquake in 2016 in the center of Italy. Please, next slides. So here in these slides, we have on one end the seismicity of the central Italy, for a 450 years return period. So this is the expected PGA at any given site with a resolution of 1 kilometer square. And on the right-hand side of the slide, instead, we have the recorded spectra at location and instrumentation near the city of Norcia for that particular event of 2006. Please, next slide. And using FAMIVE, on one end, we have derived, as we went to do a studies in Norcia, so where we classified all this number of buildings, and for each of them, we determined the level of damage on one end. So this was an empirical collection of data using, again, rather than doing a very detailed survey of each single building, we use an omnidirectional camera to quickly collect large amount of data in a relatively short period of time. We then use that data with FAMIVE in order to derive the capacity curves, as I've mentioned earlier. And then from here, by intersecting each of the capacity curves with a large number of natural spectra, indeed 22 different of them, we can then determine, and these are scaled over a large number of, these are then scaled over a large number of points, over a large range of spectral accelerations and PGAs. We can then define what we call the performance point, as illustrated in the figure here at the center, and then from regressing the performance point distribution, we can obtain the fragility functions. This is, again, we have already provided detailed training material on this particular procedure, so please go back to our pages if you want to refresh yourself. I don't need to spend more time on this, but please, Sana. Yes, so, and finally, we through this method, we can then generalize the information that we have obtained in for Norcia, for instance, to several different small city centers, such as Norcia, more or less medieval cities, not just in Italy, but also in other parts of Europe, which have similar constructions. And so use these fragility curves using the log normal model. For instance, in this case, considering different level of ductility according to the GEM, the taxonomy, and different level of height. A similar approach, next slide. We use for the city of Valencia, as I mentioned earlier, so in particularly the Pla Remei, which is this neighbor seen from the sky, please. And again, we identified a number of typology. We define here a larger number of capacity curves dependent on different uncertainty that we had about some of the parameters that comes into the FAMIVE analysis. And by using this, next slide, we could then define very detailed analysis, very detailed fragility functions for different level for different number of 4, 5, or 6 stories. Again, using exactly the same approach, and ultimately, yes, please, the next slides. Ultimately, going into providing through the MEDiate project reliable fragility functions that can be used by that are expressed in terms of the median level and the standard deviation, the two parameters alpha and beta that Pierre was referencing earlier, and that have in their description sufficient indication of the specific typology of used so that people can apply it. For instance, in this case, in many parts of Southern Europe, where this type of 19th century and early 20th century masonry buildings can be found in many cities. And with this, I think, yes, this is the same for the fragility, for the 2 and 3 story height buildings made on stonework coming from Norcia. And with this, we can conclude my intervention. Thank you. And I think it's down to Costantino, please. Perfect, Costantino. We can see your slides. Thank you.
So, hello from me too. I would like to thank Professor D'Ayala for the invitation to this webinar. I'm also working at the BERGEM, the French Geological Survey, and I will be talking about damage state dependent fragility models for reinforced concrete buildings in the case of flood and earthquake hazard. So as we saw in the first presentation today, in multi-hazard risk analysis, we have two kinds of interactions between hazards. We have the level 1 interaction with respect to the intensity of the hazard actions, but our work comes in with respect to level 2 interactions with respect to the consequences of the hazards on the buildings. And simply put, this has to do with the cases when a hazard acts on a building, causes some damage, there is an existing damage because of this hazard, and then we have some other hazard that will act on this building which has some damage, and most likely it will cause more damage than it would cause if the building were undamaged. So in terms of fragility curves, this means that fragility curves shift or move towards higher probabilities for the same intensity measures. So the objective of this work was to develop a damage state dependent fragility curves, also fragility curves also that depend on the type of hazard that causes the loading on the building. And here we have the layout of this presentation and the layout of this work. First, we'll talk about how we simulated the back-to-back hazard actions on a building model. In this case, the hazards are earthquake and flood. Then we'll talk about how we modeled the building model that we used for this study. And then we'll explain the calculation of the fragility model parameters, and then we'll see the effect of the initial of the existing damage state on the seismic fragility curves. Then we'll see the effect of the way we model structural degradation on the seismic fragility curves. And then we'll talk about the effect of the type of hazard that has caused the existing damage. In order to model the interaction of hazards with respect to their consequences, we use the classical back-to-back analysis. We had a first loading step with one of the two hazards, earthquake or flood. This was random. And then we had another loading step with another hazard. Again, this was random. And as far as the earthquake loading is concerned, we used unscaled ground motions from the European Strong Motion database. We filtered the database with this criteria, and we ended up with about 300 records. And in each step, when the loading was in strong motion, we used randomly we picked one of the two components of the record, and then we did not use the other component. In the case the same ground motion came up, it was rejected, and we kept looking for another type of hazard for the step 2 to avoid using the two components in the same analysis. And in the case of flood loading, we applied hydrostatic and hydrodynamic loads on one side of the building, which also were random. And based on this scheme, we created 10,000 loading time histories, which we applied to a 2D building model of a reinforced concrete building with masonry infills. This is a moderate cold building, which is common in the area of Nice. So the simulations, the 10,000 simulations we did are time history analysis, but we also did a pushover analysis just to first to get a sense of how the model compares with other existing similar models. In this case, we have the pushover curves of two similar models in the SRM20, but mostly in order to determine the thresholds of the damage states. And we used the definition of the damage states proposed by Martins and Silva and their equations. So we expressed the pushover curve in terms of the maximum interstory drift, and we, based on their formulas, we calculated the thresholds. As the ultimate displacement, we assumed this ductility ratio proposed by Hausus for low-rise reinforced concrete buildings with masonry infills. And then we did 4 different varieties of this building model depending on the structural degradation in the model. The first model didn't have any pinching in the moment and curvature loops. The second one had pinching. This can simulate the pinching due to, let's say, somehow inadequate transversal reinforcement. The model 3 introduces strength degradation, and this type of strength degradation depends on the ductility, on how much inelastic deformations we have. And the fourth model also has strength degradation due to the energy dissipated in a cycle of loading. So we did the simulations, and for those 10,000 simulations, and in order to calculate the fragility curves, we took the intensity measure, the ground motion intensity measure, which in this case was the PGA, and the other data that was given to the regression was an ordinal categorical variable with respect to the damage state. So here we have the classical equation for a log-normal fragility curve, and with J capital we have the number of damage states, and J is a counter. So we express the fragility curve with this equation. For example, in the case of damage state 3, we would have the complementary of having this categorical variable, which is equal to 2 or 1. Which corresponds to damage state 3 or higher. And then we use a generalized linear model with a probed link function, which is the model that is being solved. And for example, in the case again of damage state 3, this would give us the P3 and the P2 and the P1, which then we would add up in order to get the probability of exceeding the threshold of damage state 3. So the generalized linear model calculates those parameters, the A and B, but those are not the median and the dispersion of the fragility curve. And then we do a very typical change of variables. here and here to get the median and the dispersion of the fragility curve based on the parameters given by the regression. At this, so here we have an example of such parameters, and as we see, these are not the ones we use as median or dispersion, but we also get the standard error. So if we need, we can have the uncertainty in the parameters of the fragility curves. Now, again, the dispersion that we have got at this stage, it's the dispersion only due to the variability in the responses due to the seismic excitations. And then we're adding two more empirical components with respect to the uncertainty in the threshold of the damage states and with respect to the uncertainty in the capacity. Another alternative would have been to model those directly in the simulations, but we chose to use this solution in this case. And then by modifying this, we end up with a classical equation for the fragility curves. And here we have the results for the 4 varieties of this building model. And we also have the parameters for the 2 similar models in the SRM20. And as we see, as we add more strength degradation into the model, the medians of the fragility curves are reduced, but also we end up with somewhat higher dispersion in the fragility curves. So let's take a look at the effect of the initial of the existing damage state in the fragility curves. So here we see the results where in the first loading step we have either a flood or earthquake. We don't separate the two. And we take the responses from the second loading step and we calculate the fragility curves for damage state 1, damage state 2, 3, and 4. And for example, here we see the fragility curves for damage state 2, considering that the building is undamaged. This is the red or the orange line, and considering that the building already is in damage state 1 due to the loading in the first step, which is the green fragility curve. And as we see, it has shifted towards higher values. So we see that the building is more fragile, more vulnerable. And the case that really sticks out is the case here for damage state 4, in the case that the building has already extensive damage. So we see that in this case, the building is very, very likely, much more likely to have damage, to have a complete damage compared to the other cases where the building has moderate, extensive, or no damage at all. Again, we also saw the value, already seen the values in the table, but here we're doing this comparison graphically. So we have bars giving us the ratio of the median of the fragility curve in the case for damage state 2, damage state 3, and damage state 4, considering that the building already has a damage state 1 or damage state 2 or damage state 3. And we have the 4 varieties of our model. And the 2 varieties, the model 1 and 2, that do not have strength degradation pretty much stay equal to 1, which doesn't seem very reasonable, but the models 3 and 4, which include strength degradation, lead to much reasonable results. We see the reduction in the median of the fragility curve. So we see that the building becomes more fragile when it has an existing damage state. And I would just like to note that in the cases where the ratio is a bit higher than 1, it's just because of the uncertainty in the estimation of the parameters. And now, with respect to the type of hazard that has caused the initial damage, here we have the seismic fragility curves based on the responses in the second loading step for damage state 2, 3, and 4. When the building already has initial damage state 1, 2, or 3 due to the loading in the first step. And we have the fragility curves in the case that this existing damage was caused by flood with the blue line. In the case when this damage state, the existing damage state has been caused by earthquake, the fragility curves are given with the red line. And we see that the fragility, there is a difference between the two. This is the important message here, that at least in this case, the type of hazard leads to different results. And in the cases that the damage has been caused by earthquake, the building is more fragile. The fragility curves take higher values. So to sum up, we saw that we need to model, it seems that we need to model the strength degradation in order to model properly damage accumulation. And we saw that there is a difference in the fragility curves depending on the type of hazard that has caused the damage. We presume that this is due to differences in local structural degradation. And as we saw in the first presentation, damage state-dependent fragility curves may be used to model cumulative damage or damage during an aftershock sequence or during the life cycle of a building using Markovian approaches. And then if our finding, the fact that the fragility curves seem to depend on the type of hazard, maybe these approaches need to take this fact into account, for example, in their transition matrices. I would like to thank again Professor Dayala for this invitation. I would like also to thank the MEDiate project where Pierre Giel, Caterina Negulescu, and I have done this work. So thank you very much.
Thank you very much, Costantino. And yes, all the work that we are presenting today was in the MEDiate, within the MEDiate project. And the idea is that all these framework for fragility functions, again, it's first of all applicable to the wider European community, but also the fact that then can be used in process in a platform that we are developing within the MEDiate to determine the consequences, very different type of consequences and impact when this event takes place, so that authorities then can define scenarios and they can make decisions on the basis of the models that are intended as support to this platform. And with this, I think the presentation goes, the microphone and camera goes to Caterina Negulescu, please. Thank you again, Costantino, for keeping to time. Caterina?
Hello, I'm just
Yes.
in the other room because I have a problem with my. So I'm coming. Pierre is trying to share my presentation.
No worries.
Okay, thank you very much. Thank you for the invitation and for the organization of the webinar.
Welcome.
Okay. It's okay for, can you see the presentation?
Yes, perfectly. Thank you.
Okay, thank you very much. So my name is Caterina Negulescu. I'm from French Geological Survey, as Constantinos and as Pierre. I'm speaking here about very specific case study. It's an application of an earthquake that is followed by a tsunami. So it's really very specific. So in our case study, the earthquake make damages to the building, and then tsunami come just after. So impact of tsunami, it's on the building that are already damaged. So the case study that we present here, it's located in French West Indies, in two different territories. A part of Guadeloupe Island and another territory is the Martinique Island. And we inspired for the earthquake hazard, we inspired from two historical earthquake that occurred in 1843 in offshore of Guadeloupe and 1839 in offshore of Martinique. Okay, so this is just to make a position of our study in a more general context. We can see here several steps that we need for a scenario. So on the top of the figure, we can see a single hazard case in which we have an hazard event and then an intensity measure of failure mode damages and functionalities. So when we don't have a cascade scenario, we can have just one single hazard. And then we can go to one intensity measure and so on. In our case, we have a cascading hazard case. So in this case, we have hazard event for us, letter 1, H1, it's the earthquake, and H2, it's the tsunami. So for the earthquake, we can have several intensity measure. So we can have acceleration or peak ground acceleration, spectral acceleration, velocity or intensity. And for the tsunami, we use water depth and water velocity. So in this case, we have done the first calculation from the earthquake hazard to the earthquake damage. And then we just update the exposition considering the damages due to the earthquake in order to consider that the building are already impacted when the tsunami arrive in the area. So we don't work in this part related to the functionalities. We have here two different approaches that we try to compare in our study. The one that is in the left is the HAZU tsunami model, and we see here that they are doing two parallel calculations and they are summing the probabilities at the end. So they are doing earthquake hazard analysis, considering inventory of exposure and vulnerability, and then they have earthquake damage assessment. And in parallel, they have tsunami hazard analysis and tsunami damage assessment. And then they are using a formula for combining damage state probabilities from earthquake and tsunami. So in the right part, what we have done, we have used the first calculation, like in HAZUS, from earthquake hazard analysis, we go to earthquake damage assessment, considering inventory exposure and the vulnerability for the exposure. And then once we have earthquake damage assessment, we go back to the inventory in order to update exposure and the vulnerability, considering the damages that we have after the earthquake. So we update in two ways. The one is related to the collapsed building. So in this case, we just don't have anymore the collapsed building, and we consider an update spatial exposure. And the second way is considering damaged buildings. And in this case, we are just making a lower resistance of this building for the second hazard that impacted the building. And then we have tsunami vulnerabilities taking into consideration the damage coming from the first hazard from the earthquake. So I'm going straight to the results, and then I'm go back in the presentation to explain how we arrive to these results. So here we have for the territory of Martinique, we have the results from the earthquake inspired from 1843, which is located near Martinique. So the first line, we have the damages in slight, moderate, extensive, and complete, just for the simulation of earthquake. The second line is the damages just from the simulation of tsunami. And the third line is the combination of both earthquake and tsunami using HAZUS formulas. And the last one is our study. So we can see that we have a trend of having more percentage of complete damages. And in this case, we have less extensive damages. So we can see that HAZUS combination is more or less a summation of collapse damage from earthquake and tsunami. And in our case, the collapse damage is much more than a summation, because in fact we consider the vulnerability, reduced vulnerability. So for the same conclusion we have for Guadeloupe Island, and for the same earthquake, 1843. And here we have much more damages, because we are just zooming on the area very impacted by the tsunami. But the conclusion is almost the same for Jesus addition of the probabilities. We have almost just summation of the collapse from earthquake and collapse from tsunami. And in our study, we have much more percentage of complete damages and less percentage of extensive damages. So what we have used for the earthquake, as I say, we have used a large megatrust event offshore Guadeloupe. This is referred as the interplate offshore Guadeloupe, and this is inspired from the location of the earthquake in 1843. However, we know that this historical event induced only very small tsunami. So in this case, we inspired from the location, but our tsunami, it's big one. And the other one, it's also another earthquake inspired from the location of 1839 in Martinique. So we can see in this picture with the red star, we can see the location near Martinique and the other one near Guadeloupe. And we can see in the table the characteristic for the earthquake calculation, also the attenuation law and conversion between acceleration and intensity. So we try to make a comparison between the historical observation. We are lucky to have a database on historical observation in French Geological Survey. So we can see on the left that during the 1843 earthquake, we have historical observation of intensity 8 to 9.5 in Guadeloupe, and the same earthquake make intensity about 7 in Martinique. And in the right part of on the screen, we have our intensity that are modeled by us. So we can see that we have more or less the same range of intensity. And we can also see that for Guadeloupe, we can see the separate part between intensity 9 to 9.5 and intensity 8 to 8.5. So we cannot see that it's validated, but we can see that we have almost more or less the same range of intensities. For the tsunami hazard, so our colleagues that are working on generate and propagation of tsunami provide us maximum sea surface elevation around Pointe-à-Pitre and Guadeloupe for the both event. And for tsunami hazard parameter, maximum flood depth, we use this parameter. So in order to have this parameter, we have the surface elevation minus the typography. Now here we have the pink line that it's related to the hazard parameter for both earthquake. So exposition, we had a project in these two island, and we have the repartition of the different typology. We have 25 typology in French West Indies, and we have like homogeneous vulnerability census block. And we can see that for Martinique, we have around 3,000, and for Guadeloupe around 2,000. So this typology was evaluated after field trip during several years before this project. So these are quite representative for the typologies in the area of study. So what we have done in order to combine earthquake and tsunami, we have used two different approaches for the vulnerability index for earthquake calculation and capacity curve for tsunami using Jesus methodology. So what we have done is that we update vulnerability properties for the damage for the structure that already damaged, and so the intact pushover curve is reduced in order to have less resistance and also less rigidity to the structure that already damaged in a certain damage degree after the earthquake. We also have some observation on real building after the earthquake in 2007. So here we have 4 different buildings, and after this earthquake, they were damaged in different damage degree. For example, building 3, it's in damage degree 1, so no structural damage, and we have a frequency around measured frequency of 0.429. Building 1 and building 4 are in damage degree 3, so moderate structural damage, and we see that the frequency is less, so 3.9. And building 2, it's in damage degree 5, so very important, and some collapse in structural elements. So we have a frequency of 3.4. So this is very important study, because we have really, we can see here the lower frequency for the damaged building, so the higher period of the building. So you use this information to calibrate the reduce capacity curve. So for the tsunami, we use a lateral force due to the tsunami flow. And here is based function of the hydrodynamic force and also the density of debris flow material and drag coefficient. And we have also the lateral capacity of the building, which is function of the ultimate yield and ultimate force, and multiplied by the total weight of the building. So we have done this for each census block and for each typology. For example, here we have typology 1, we have the vulnerability 1, so the vulnerability, intact vulnerability without the damage. And then we have the earthquake analysis, and we have this typology can have 5 damage degree and no damage. And then we are using this damage degree for making a new vulnerability depending on damage degree. And for the second step of analysis, we have vulnerability 1 for damage degree 0, so intact building. And then we have vulnerability 1 for damage degree 1, and so on. It's quite similar with what Konstantinos just presented before. And we have done this for all the typology and all census block. Here we have some mapping results. So here we have the inundation on the Ponta Pietra, which is the area impacted, more impacted by the tsunami in Guadeloupe. And here we have also mapping results just to compare results from tsunami and also results coming from cascade, earthquake, and tsunami after. And we can see here that of course the area with complete damage are more extensive in the right part of the screen, which is normal. Here we have the same results, but as maybe another represent number of building for moderate, extensive, and complete damages. In the case of tsunami in gray, and in the case of cascade and tsunami, we can clearly see that in this case we have complete, extensive, and moderate. That is much important in the case in which we consider the damages coming from the earthquake. And also we can see on the mapping results the same conclusion. And this is the same results, but in this slide it's about the territory of Martinique, using the earthquake that it's occurred in Guadeloupe in the left, and then the earthquake occurred in Martinique in the right. So we can see that in the left we cannot have so much difference between tsunami and cascade scenario, because in this case the tsunami coming from Guadeloupe do not impact so much the territories in Martinique. So in this case we don't have so many difference. But in the right part we also see that we have differences. And here, what is interesting is that contrary to the other results, we have more difference related to the moderate damage degree. So just to the conclusion and also to ongoing work and perspectives. So this is a very specific case study. So conclusions are quite important, but of course cannot be generalized. So should be taken with attention. What we would like to do to the end is it's globally to build an integrated modeling strategy from the co-seismic tsunami generation and also propagation, and then flood and tsunami exposure and impact. So we will like, because in this case we have the tsunami generating and propagation that is done by some colleague with some software, and we are using the output of this step as input in our step. So we would like to have a integrated modeling strategy. Also relating to our part, maybe improve method for treat two phenomena that have a difference in the scale of impact, because of course the impact of earthquake is much more important all the surface of the island, and the impact of tsunami, of course, it's less. The area of impact is less important, so it's quite complicated to compare when the scale of impact is different, and also intensity of damage is different. So for this study, we have done several assumption, and we should make some correspondence between the earthquake and tsunami typologies, for example, and also because between earthquake and tsunami damage degree. They could be the same, but also they could be different. So we should make some choices in our study. So it's important to have this workshop and go further on this multi-hazard risk assessment. So we use two different approaches for calculate the damage. So it will be interesting to have a cascade earthquake tsunami fragility curve instead of reducing the capacity curve as we have done. And also we can better use the influence of debris of the collapsed building. So in this case, we did not change this parameter. And I continue to work on the vulnerability for a multi-hazard risk. This is very good. Thank you very much.
Thank you very much, Caterina, for these very interesting applications. I think it's the first time that I see such an in-depth analysis of tsunamis and earthquakes effects considered with historic data in these details. Now we are moving to a slightly different subjects. So Nadisha, please, if you want to start your presentation, we will look at the social vulnerability and the impact that the social vulnerability have on communities. Thank you. In fact, social and economic, I should say.
Can you see and hear me okay?
Perfectly. Thank you.
Thank you so much. Thank you, Professor Diala, for the opportunity. I'm Dr. Nadisha Niwanigaratna. I'm senior lecturer at Anglia Ruskin University. I'm a construction economist by background. In this presentation, I will be talking about social vulnerability to disasters, so extending the physical damage modeling talked about by previous speakers. Before I making a start about social vulnerability, I would like to share 3 stories with you. This is Chaos' story. She's a 6-year-old girl. Her house was completely damaged by a recent typhoon in Vietnam. You can see she's collecting her toys from her collapsed house. So based on the picture, you can say it's built using typical materials. So based on the modeling method explained by previous speakers, we could model reasonably well the damage to this type of building. But what we didn't know was about Keo, or what she cares about, or what she would lose as a result. The next story is about a missing out community in Northeast India. So in Northeast India, there's Brahmaputra River, when it gets flooded, this community suffer devastatingly. They could lose lives and they could have damage to their properties. In order to respond, they have come up with this houses called Changa. Ga in their language refers to houses. So Chang is a stilt. The Changa refers to houses built on poles. In this next picture, you can see what is inside a Changa. And in the quotation in the middle, you can see one of the residents explaining what is inside them. He explains the fireplace. He explains where he stores his food. He even talked about a balcony-like extension. So without looking at these pictures, if you imagine this description, you would possibly imagine a tree house you would like to go on holiday, not a house of this type. The next story is Bimala's story. Bimala is a 40-year-old woman. She lost her house to 2015 Nepal earthquake, which we all probably have read a lot about. She has received 300,000 Nepalese rupees to rebuild her house. 300,000 Nepalese rupees is equivalent to about 1,700 sterling pounds, or about 2,100 euros. So for someone who is well off, it is not unaffordable. But you can see from Bimala's conversations, it is a life-changing experience for Bimala to rebuild her house, which she would not be able to do otherwise. So these three stories nicely leads me to explain you what social vulnerability is. The definition of social vulnerability is the susceptibility of exposed individuals or communities to the adverse impacts of natural hazards. So social vulnerability can cause disproportionate deaths, injuries, or disruptions. This can impact their ability to prepare for a disaster, their ability to respond to a disaster, or act during a disaster, and their ability to recover from a disaster. So yes, we all know about this. So let me explain a proper list of vulnerability dimensions. So age can act as a vulnerability dimension. Researchers consider people of young age and elderly population, especially anyone younger than 5 and anyone older than age of 65 as vulnerable, because they have limited ability to move around during a disaster or to do any preparation. So gender researchers normally consider female population are more vulnerable to disasters because they are limited physical and psychological strengths, as well as they are limited economic status due to some of them may not be working, or they may have house costs and other things to pay for. Ethnicity is related to a number of things. It could be linked to the race, it could be linked to the immigration, could be linked to their language barriers. So racial discrimination and related pay gaps can cause income inequality, so can affect their ability to prepare and respond to disasters. The language barriers, for example, can limit their ability to understand the information or access the support they could otherwise have if they knew all the information in their local language. Economic status, think about Bimala's story. So in this part of the world, we are increasingly building earthquake-resistant buildings. What made Bimala not do in her building originally, making it earthquake-resistant? Because she couldn't afford, she was poor. Disability, similar to the age, we consider disabled people have limited ability to move around and prepare and recover from disasters. Tenant type is whether our houses belong to us or whether we are renting. If we are renting our houses, we have limited or no right to retrofit our houses and to prepare for our disasters. It is also said that sometimes renters are reluctant to take actions to minimize damage because the houses belong to different people or not them. Educational level can mainly be linked to the employment ability and pay gap, as well as people's ability to understand information and access resources. So these are the typical dimensions or vulnerability dimensions that could make someone vulnerable to disasters. But are these universal? In the picture on the left, you can see it's a photo taken during a preparation program in Japan where they prepare their children to respond to earthquake early warning system. Japan is an earthquake-prone country, so they have regular programs to help their children to and other people to act for these early warnings. But let me tell you a fact. During the 2011, sorry, I'm going to that one. During the Emilia-Romagna earthquake in Italy, the researcher says 33% of people waited in their bed. So they were not elderly people or they were not very young children. They were people who were able to move, but they didn't. So the picture on the right is a farmer from Greece, and he is working outside in extreme heat. From farmers and tour guides, millions of people are now work in extreme heats during summers, and it could cause heat stress and could even lead to strokes. So he is not vulnerable looking at him because of his age or because of his gender, but he is vulnerable, and millions of people are vulnerable because they are working outside. So other than typical dimensions, what I wanted to stress here is there are contextual issues that we need to consider when we talk about vulnerability. So let me summarize. How do we assess this? We know all these stories, but how do we really assess this to use them in decision making? So there are quantitative studies by social scientists. The stories I shared at the very beginning are things like that. So people can speak to victims from past disasters, collect their experience to understand how these people disproportionately affected by the disasters. These things can form very useful information to produce later population studies or quantitative analysis later. The second type is quantitative or retrospective assessments of disaster impacts. This table here, for example, was done by Elena Sutley and her colleagues based on 1994 Northridge earthquake data. They have computed how vulnerable groups have odds of having more injuries, more fatalities, and more post-traumatic stress disorders. In this particular example I highlighted here, you can see the female population have a more than twice chance of dying due to an earthquake of this size. The last type is place-based assessment. It is what you can say something like here. The place-based assessment is normally is related to an index. So it does assess the relative vulnerability of a population or of a place. It could be a city or it could be a region compared to the neighboring properties based on the characteristics of that place or the city. So this is the type of work we continued during the MEDiate project where my previous colleagues explained. So there are three different types of vulnerability assessment methods or indices we can use for decision making. The first type is social vulnerability indices, and that purely consider the vulnerable population or extent of vulnerable as people living in a particular place. Or it could be the percentage of female population in a place, or it could be a percentage of low-paid people in a place, or it could be a percentage of disabled people in a city or a region. The second type is called socioeconomic status indices. You can see I have underlined the term status here. In this one, in this type of indices, we do consider not necessarily the vulnerable extent of vulnerable population, but we consider the average status of a place based on typical vulnerability dimensions. For example, in the first type, we might consider the percentage of young children in a place. But in this socioeconomic status indices, we would consider the median age of a city or a place, the median income of a city or a place. The third type is disaster resilient indices. From the name, you can possibly judge that it's not necessarily related to the vulnerability, but it is related to resilience. So resilience indices measures a community or a place's ability to recover resilience from a disaster. So it does include some aspects of vulnerability dimensions, and also it also includes other aspects related to environmental vulnerability, physical vulnerability explained by previous colleagues, as well as institutional capacities and the things. So this slide that show some of the social vulnerability indices we developed during the MEDiate project. So we did develop a social vulnerability map for Essex, UK, considering the flood as a disaster type. So that's the picture on the left. You can see the red wards are the most vulnerable people live, and green are the places, those wards where least vulnerable people live. And the one in the middle is the social vulnerability map for Nice in France. We developed that one considering the heat wave. So if you can remind or rethink of the story of the farmer, you can see the working outside could lead people to be vulnerable. So some of the red areas here is related to the population, farming population, and people working outside. The last picture here is the social vulnerability map for Oslo, Norway, again considering flood as a disaster. So these are the results. So I did show you the results first, and I am going to briefly explain you the steps of calculating or developing this type of index. The first, you need to define what the spatial level is. You could do it at postcode level or at ward level, at country level. It really depends on what is the purpose of that map or what decisions you are going to take. The one in this map is at ward level or electoral ward level, because we wanted to understand how funding can be allocated between wards based on these vulnerabilities. So once you understand the spatial level, then you can look at data. First, you need to find publicly available data. Most of these indices are developed based on publicly available data, like census data or other population survey data. You can locate this data, and then you need to understand, or you need to filter the indicators that you can use as proxy to identify each vulnerability criteria related to your case. You need to understand the female population. You need to understand how many children under 5 living in each ward, or how many people under 65 living in each of these wards. So this may not be any straightforward calculation, even though I have listed it as one step. But you might need to transform your data or aggregate your data to get to some of these numbers. So once you know this, the number of people related to each vulnerability dimension for each place, then you can compute percentages. As a percentage, how many under 5 children live in each place. As a percentage, how many disabled people live in each state. So that's the next step. When you have the percentage, then you need to nominalize data. So your population, total population of each ward or place is actually different. So you can nominalize it by converting to z-scores either using min-max nominalization method. So you can compare them across the places or across the counties. Once you have the z-scores, you can aggregate them to calculate or compute the aggregate vulnerability score for each place, or in this case, for each county, and that can tell you the relative vulnerability of a place. In my case, it's a relative vulnerability of a county compared to other counties. So you can understand in these places, in red places, we have lots of people who are more vulnerable to the selected disasters compared to the other places. So you can use this data together with the physical vulnerability modeling to understand or make decisions or to do further analysis. Finally, I would like to thank the MEDiate Consortium and ARU MEDiate team. The research does not happen individually. It involves thinking and collective minds of lots of people. So thank you, everyone. If you have any questions, you could email me the questions, as well as I'm happy to answer them now. Thank you very much. Thank you, Gina, for the invitation and opportunity as well.
Thank you very much, Nadisha, for keeping to time and quickly illustrating a very critical aspects of communities' vulnerabilities. Maybe also the other speakers can now open their cameras and mic. We have a few questions. I think some we have already answered in the question and answer in writing, and we will not go over it again. But there is a question on from Shafi Hulla Makil, asking how we can rapidly get to the flood depth in an area in order to do vulnerability in urban areas, in order to do vulnerability assessment just after an event. So this is related also with rapid response, I assume. Pierre, do you want to try to give an answer to that?
Regarding the flood?
Yes, please.
Yeah, please, Katerina, yeah, if you, yeah.
Yes.
So about the flood in the urban area, I think that it depends on the method for the estimation of the flood. Because if we are using a numerical estimation of the flood, this takes a lot of time, because we have a lot of, for example, propagation is taking the hour, so we cannot have this rapidly. But what we have done in Bergem is that we have a lot of simulation of propagation that were done a year before. And then now we are using a meta model in order to estimate based on this long time calculation simulation. We are using meta model for estimate the flood quite rapidly now using the meta model or analog response or so on. So I think in our case, maybe it depends on this. If we make numerical modulation, it takes a lot of time, because this need a lot of calculation needs. And if we are using approximative estimation, this could be quite rapid if we are using meta model or these kind of things. But maybe there are some other method for estimation.
Thank you very much, Caterina. And of course, you are deriving those flood depths from measures of rainfall, so given by the Met Office, or given. So you need to have a model already developed, in other words, that correlates the water, the rain to the flooding.
Yes, of course. In France, so we are using the National Institute for Meteorology for giving the input data, and then we are making the calculation. Of course, we need all this information, of course.
Thank you. Thank you very much. So there is a question about what about fire and drought hazards by Richard Hughes. Yes, they are both very relevant hazards, but they were not the main identified hazards in within the MEDiate project, and so we have decided not to consider them for this particular project and for this particular presentation. I don't know, Pierre, if you want to add anything.
Yeah, because well, one of the hazards that was considered in one of the MEDiate scenarios were droughts.
Yes.
But I think it's quite difficult to relate it to, let's say, physical performance of structural systems, for instance. But maybe one way is quite maybe still quite a let's say a threatening hazard is for especially we have this in France is this story of shrinking and swelling of clays that are below the buildings. And if you have long cycles of let's say extreme rainfall and then extreme droughts, then you have a lot of adverse effects on buildings
Yes.
because of this. So this is maybe the one thing you have to look into, yeah, when you are considering drought hazard is this yeah.
Yes, this
of the clays,
alternance of drought period and then
Yeah.
important road flame. In countries and in areas with shallow foundations and superficial clays, for instance, in quite a few parts of the UK in that respect, droughts can bring shrinking of soils and then failure, foundation failures or cracking, especially in masonry structures with shallow foundations where you have movement. There is some anecdotal information about this, but I haven't seen any consistent study that has actually gone to the extent of deriving fragility functions that correlate the extent and length of a drought period to then the corresponding shrinking or heaving of the soil and therefore they correlated to the damage on the side. So that would be the next project probably. And also, yes, this was also the same question from Sandra Graus-Quevado. And she's also asking about wildfire. So I don't know if I'm not I don't know much about fires, but please, if at BRGM you have done some work on this.
No, we have sorry, we have no expertise really on wildfires. I would not say anything wrong. So, but yeah, you are right. Yeah, these are hazards. That gain a lot of importance now. It's yeah.
Yes, we have to pay attention on this on the future, but we start to just be interested.
Yes, exactly. They are increasingly relevant and related to climate change. So yes, they are becoming very quickly a very important hazard. There is a question from Professor Daya Shankar about who is the person responsible for declaring the alarm and the early warning, I assume. Or is referring to are you referring to the early warning, or maybe just to determine that a region is vulnerable to earthquake, landslide, or floods? Each nation should have a level of hazard mapping that then governmentally it's agreed upon and has a certain level of seismicity or a certain recognized level of flooding and landslide. When a flood or a land or an event occurs in a particular region, there is always a lot of political discussion on whether that particular region had been previously declared at that level of intensity of that particular hazards, such that people should have been prepared. But in many developing country as well as developed country, urbanization is taking place in areas that we are already well known as to be at risk of flooding or landslide. And the community is willing or unaware of the level of risk. So it's really an issue of communication, I think. I don't know if Pierre, Katrina, Costantino, Asana, do you want to, in fact, Nadisha, do you want to add anything to this? As you were providing.
Just a confirmation about what you said. Yeah, I think each country has
Yeah.
a system, some procedure to make, and it's quite politic procedure. So we go up the information, and then there is a real procedure in order to make the alarm. So we don't have really information about this, I think.
Maybe I can add that I think really for weather-related hazards, like it can be, let's say, now it is expected from people usually to have warnings. You know, you have all these weather agencies, local, the policies. Everything is quite. And this is maybe not the case, you know, for geo hazards, which are, let's say, not. Of course, we don't have the same methods. You don't have the same time frame, of course, and this is maybe also a bit a difference between these two worlds, I would say, and yeah. So maybe there is also work to do on this matter. Yeah.
And with respect to tsunami, sometimes there is an agency, let's say like an observatory that uses sea level gauges in order to give some warnings. But with respect to earthquake, I think it's mostly down to the civil protection mechanism and to the local authorities to declare an emergency given to the damages that they have observed.
Yes, exactly. Yes, and then to trigger a rapid response after that. Thank you, Costantino, for that clarifications. There are another couple of questions from Richard Hughes. We will go first to the issue. This is relevant to Nadisha. Richard was suggesting that to the list of vulnerability factor for people, he would add the skill level. Nadisha, would you like to comment?
Thank you, Richard. In most cases, skill levels is captured at educational status. So in the UK census data, I would say how many people have a level 3 qualification or level 4 qualification or any other. So normally skill level is captured in there. If you are thinking of different skill levels for people, if you are thinking of a skill level of people just dealing with those things in the community, we would assume if a community has suffered floods or earthquake in the past, they all have similar experience. And in case immigrants will then have a disadvantage impact because they didn't know about past event or information about that. So it is captured in one of the two. I hope that answers. Thank you.
Thank you. Yes, but sometimes skills are not necessarily related to education, no? They might be related to experience, which might be very valuable or invaluable, depending irrelevant of the education. So it would be interesting to see how one could use it in a more rounded approach. And Richard still has another question about fires in earthquake, which yes, is very, it's relatively common. Yes, we think of the earthquake in 1755 in Lisbon that triggered a fire that destroyed 2/3 of the cities. And he's recalling both Japan in the early 20th century. This is the Tokyo earthquake, and then Yemen in the 1980s. The issue of how how fires develops after earthquakes, well, there is less evidence of this happening in recent earthquakes. So in recent urban conditions, timber is much less used now than it used to be in construction. At the same time, timber is now coming back in constructions in several places for sustainability purposes. So maybe we should start thinking again about how we prevent earthquake following fire following earthquake, but also, of course, it has to do with open flames, with the distribution of gas and fire triggers, basically. Which could be also electricity, of course, cables and so on. I don't know, Pierre and Katerina, again, what is your experience?
Yeah, I mean, there is a, let's say, maybe I would speak also of let's say on a wider area, from a wider area point of view, not just the structural system, but also let's say, the whole city. If
Yes.
now, for instance, in Japan, they have system also to shut down gas networks automatically and so on. So this also limits a lot, you know, the gas leakage and so on. And also maybe another aspect then is also to assess also the, let's say the performance also of the water network, especially water networks for firefighters and so on, if they can quickly access, you know, this these water appliances to to fight the fires quite efficiently. Also, this is there are studies like this also on this on these topics. If you,
We have gone, I think, a few minutes beyond our set deadline of 4 o'clock. There is somebody with a raised hand. I'm not sure who it is. I don't know if you have already put your question in typing, or if you want to have a quick, if that hand was raised by mistake, or if you wish to say something, then let us know so that we can open your microphone, please. But you need to write it in the in the chat. Otherwise, thank you all for participating. Thank you to our panelists. Very interesting also, all the presentations and the discussions. And thank you, as always, to our audience for the interesting questions.
Tina,
and with it, I think,
open the mic.
yes.
I don't know if you want to hear his question.
So please, do you want to say who is it? Rafa?
Yes, Sergio
Can you
Dante.
say who's the person? Or can you introduce them? And
Sergio Dantas, he raised his hand, but and you mute himself. Sergio, I don't know if you want to say something.
No, sorry.
Okay.
okay, that's good. That's perfect. So then we will simply say goodbye to everybody. Now we will have a bit of a pause for Christmas, but we will see you again towards the end of January with another presentation that is indeed linked also to the MEDiate project. And with this, thank you to everybody for participating. And again, thank you to our panelists, and goodbye for now.
Thank you very much.
Thank you
very
very
much.
much.
Thank you, goodbye.
You're
Bye bye. Bye.
See you.
Bye. Bye-bye.